Well, thanks, Christoph. That was really enlightening. Really fantastic example. I think that basically was continuing Christoph actually left off with sort of venturing into another issue of architecture, tectonics. And tectonics actually are close relatives to systems, or can be actually systematically developed, let's put it that way. Tectonics, basically tectonics, the origin of tectonics are basically in the Greek language. Tecton was the signifier for the carpenter or the builder. And eventually Tecton emerged as the master builder or architecton. So what we are looking at in terms of tectonic is actually sort of the core of our profession. It's basically the art of shaping and assembling materials into buildings. So the discussion around tectonics, therefore, I think is a kind of a critical one. Also, well, I assume that about 50% of you heard my lecture last time, and it was on materials in last fall. So I didn't want to bore you, but I think what I'm trying to do today is sort of continue where I left off with materials last time. And basically, what we sort of experience right now, or what we sort of have going on as an ongoing discussion in architecture around materials, is that we have an emergence of new materials. We have a kind of very methodological research into material behavior, and basically makes a crucial difference in terms of how we look at materials, because we now actually understand why materials behave in a particular way, instead of just knowing that they behave in a particular way. And that makes all the difference. So now we can actually design with much greater predictability, and therefore we can actually build also in a much more predictable way. There's 3 books that I think are kind of critical if we discuss tectonics in architecture. There's first of all, there's Kenneth Frenton's Studies in Tectonic Culture. Then there's follow-up by Neil Leach called Digital Tectonics, and the third one by Raizo Omoto, Atlas of Novel Tectonics. And the first one was actually a reaction. Towards stuff that was emerging at that particular time at the end of the 20th century. Here we see a Greg Lynn project, and as we look at it, it looks quite rather sort of soft, kind of immaterial. It does not really have any kind of tectonic quality. And at that point of time, it was actually believed by a lot of people that it would be impossible to actually build these kind of things, or that the designer that is behind these kind of designs would have any kind of understanding of tectonics or how to build in the real world. But the proliferation of projects like this, and this is a more clumsy project actually by Greg Lynn, and the proliferation of the digital imagery was quite significant, and the impact that they had on design culture was tremendous. We were all really seduced by these kind of images. It's really hard to believe that I thought that this is really beautiful, but there it is. As a reaction to that, Kenneth Frenton was actually advocating a different approach to that, to architecture. Basically coming from the point of view that architecture is actually grounded in the science and in the art of actually building, basically in tectonics. So studies in tectonic culture was a reaction of proliferation of digital imagery and the proliferation of digital design techniques. A couple of years later, Neil Leach published Digital Tectonics, which was a reaction to culture of Kenneth Frenton's book. And what he's trying to do in digital tectonics is actually making a quite stretched argument. What he's trying to do is asking two questions: how the digital can actually become tectonic, and how the tectonic can become digital. And that seems to be rather contradictory. The digital is kind of, really grounded in the immaterial world of the computer and algorithms, whereas the tectonic is kind of a resolutely grounded in the material world of construction. So how can these two things actually start to establish a dialogue between them? What Neil Leach actually argues, and I'm borrowing his argument actually for the rest of the lecture, is that right now we are at a turning point in design culture. What he identifies actually in a number of works is a kind of a new paradigm of thinking and designing architecture, and that he names is digital tectonics. It's the computer and its impact on architectural design, and the dialogue that is actually established by trying to actually translate quite radical digital designs into the real world of tectonics, that is actually triggering a number of really interesting developments in terms of programs actually being used to support the process of building, rather than programs being used to illustrate or represent architecture. So now, I think this is something that we really have to understand fundamentally. This is that if we look at a drawing, is a drawing actually done to actually represent architecture, to represent the final product once it gets built, or is it used to actually define a form, define a geometry, define a tectonic element? Is it used to actually construct something? Or is it used as a kind of a representational tool? Let me go back to Kenneth Frenton for a moment. What we see here is basically kind of the classical, or is a kind of a classical representation of other Greek architectural elements. Frenton argues in his book actually that in 19th century something really significant happened in architectural theory. He identifies it as the primary of space in German theory of the German aestheticists like August Schmarsow or Adolf von Hildebrand, Gothic Semper. That was later carried on actually into modern architecture, and it coincided with space-time models like Georg Riemann, a mathematician, or Albert Einstein. And Siegfried Gideon in Time, Space and Architecture, for example, clearly formulates this kind of modern paradigm of space in modern architecture. Later in the 70s, there was Cornelis van der Veen, Space in Architecture, basically summing up the whole culture that developed around space. But what that means actually as a paradigm is that we, as architects, we rather design space, basically the hollow volume, rather than tectonic elements that would actually describe the empty volume around it. So the paradigm of space firmly established the volumetric character of architecture as a spatio-plastic unity of interior and exterior space. Frenton does not deny the spatial character, but argues that space is defined by the constructional and structural modes by which it has to be achieved. So he puts a different emphasis. He says we need to actually shift our paradigm from the kind of empty volume that we define as space to the shell that actually defines the space. And by the character of the tectonics of that, we give the character actually to the space in itself. So if you look at that space here. The character of the space is basically described by its form, by its shape, but also by its materiality and how various elements are actually put together. So in principle, what Frampton argues is that architecture originates out of tectonic capacities of actual materials and not of algorithmic potentials of computer programs. So he's strongly opposed to any idea of that. As I mentioned earlier, actually software is no longer used as a sole representation tool, but it becomes actually more and more a design and production tool. Computers allow us to model material properties of architectural component, and we can actually investigate them. Like the biggest revolution in terms of digital tools happened actually in the engineering world, and there are finite analysis programs that actually really allow us to investigate the stresses that occur within particular elements of our building that actually can or have the capability of showing us the material properties, whether something behaves rather soft and fluid or whether something behaves really rigid. These engineering programs really shifted our whole perception of digital tools quite tremendously. Our architectural tools fall behind these capabilities quite a bit. They're still kind of conceived as kind of representational tools rather than as generative, investigative tools. So what that suggests actually in terms of the digital is that we can actually use the digital as a tool to rethink and redesign the tectonic. One could argue that because of the use of software, a new generation of tectonic is now capable of emerging. So now let's take that in terms of the tools that we had previously. For example, if we look at sort of kind of classical systems, like, for example, Greek architecture, we were actually basically bound to kind of predictable systems that we would establish in order to be able to actually ultimately calculate it as an engineer. So basically, what are the loads? Does it break? Does it actually boggle? And so forth and so forth. Digital tools allow us another leap forward. Now we can actually construct actually much more complex systems because we're actually having the help, the computational help of the computer to actually calculate more complex systems. So this is the big difference, a big leap, and therefore we can actually think about much more complex systems, design much more complex systems that would not be possible without the use of computers. This also means that we're sort of inaugurating a kind of a particular shift from a kind of a postmodern sensibility towards another sensibility that looks actually behavioral models of buildings and tectonic systems. That basically means we're shifting from a kind of a representational architecture where we can sort of firmly ground on a theoretical basis in postmodern architecture, sometimes also in modern architecture, to a kind of a more process-oriented architecture. And maybe we can actually attach two kind of classical examples of that. And I think we're rather bored with that slide, so I turn it over very quickly. Basically, let's say classical architecture, Greek architecture, but here's another one of these slides. But let's look at that. That's the Bank of England in London. And that's a kind of a neoclassical building. So what does it do? How does it perform? It performs on a representational level. All the columns, all the tectonic elements that we see here operate purely or are designed for a representational purpose. They're not designed as a process to make this whole thing actually stand up and work better. That is going to be contrasted actually with Gothic architecture. Gothic architecture is much more kind of a process-oriented architecture. Those buttresses are not there because they're representational, because we think they are very chic. They're there because they are actually taking loads. They're basically necessary out of a kind of a masonry logic of tectonics and elements. There's two, and what I'm trying to argue is actually that right now we're sort of at the moment where we actually maybe sense a kind of a Gothic spirit in architecture emerging in a number of projects, rather than a kind of a classical spirit emerging. Rather than representational, actually, new architecture at the moment seems to be much more performative oriented rather than representational. Both modes, I would argue, are not mutually exclusive. We always have both, but it's the way that we actually give the primary thought or energy to one or the other mode that actually makes the mixture tend or go in one direction or into the other. So what we're looking at is, I show a couple of examples that are kind of related to this kind of Gothic spirit, and where I would actually argue that these architects are actually thinking in terms, or kind of inaugurating what we're doing right now, or what we can actually sense right now, and that would be Antonio Gaudi. And here you see the floor plan of the Sagrada Familia, and you can think, oh wow, it looks like a floor plan of any kind of church. There's not something actually particularly interesting. Here's actually an early drawing. But what is really interesting about the Sagrada Familia in terms of the way that it is designed, of course it should look like a cathedral, so it has to be representational in some way. But what is really interesting is the way that it was actually designed from a tectonic logic. And of course, you probably all know from kind of structure courses that if I take a rope and I hang it from the ceiling, then the rope line is the ideal. If I would freeze it and flip it around, the rope line would be the ideal compression line of a masonry arc. So what you look at here is an early model of Antonio Gaudi's Sagrada Familia. It's basically a series of chains hanging from the ceiling, and basically by assuming a particular form, describing the form that the masonry work would ultimately later assume. So what he's doing here is actually he's computing on a kind of a material logic, the tectonic system for the Sagrada Familia. So there's no formal will from his side, sort of kind of as a primary to be sensed, or kind of a representational will, but it's actually a pure material computation that is at work here. And here's another one, basically flipped around, and here you see basically frozen chains or frozen rope lines. Here's another model of that. It's basically hanging from the ceiling. It's pure chains, and here you see a more sophisticated study with kind of weight on the ropes, and you see that the form is actually emerging out of a material behavior that is tied to the ultimate logic of masonry work that will basically then build the system of the Sagrada Familia. And here you see again kind of a hanging model, and here's the hanging model flipped around, and voila, we have a cathedral. And then later, of course, studies in terms of how it was formulated and further articulated once the overall controlled geometry would be actually found. Another exponent of kind of, let's say, Gothic thinking in architecture is Fray Otto. And what we're looking here at is actually just simple wire and soap film. And you know probably also from physics that basically a soap bubble always assumes a minimal surface condition. And that minimal surface condition is particularly useful if we think about larger constructions. And by manipulating soap film through kind of a controlled geometry like wireframes, we have a tremendous kind of potential of actually generating form. Again, form is generated here not through a kind of an act of taking a pencil and drawing on paper, but it's actually generated through material behavior. One of those minimal surfaces you will find in Munich, Günter Benisch and Frank Otto collaborated on the Olympic Stadium, and the form was found in a similar way to those soap bubble studies. Here's another way, another model that Frank Otto and Christoph Ingenhofen just recently actually collaborated. And here again you see a kind of a soap film study of that becomes a kind of a mesh weight study that becomes ultimately the kind of oculus of in the roof structure of the Stuttgart main station. And this is the thing, how it looks from the top. So what you see, what we're looking at is actually a completely different attitude. The architects here don't try to actually represent anything or try to actually aim at representational architecture, but through actually material investigation and through material logic, trying to find a form that ultimately lends itself also to a kind of a buildability, to a kind of a tectonic system. I want to now talk a little bit more about one particular example, and it's Toyo Ito again, but this time in London. And Toyo Ito and Cecil Belmont actually collaborated on that project, and it's not quite clear who was actually the primary designer on that. I would argue probably both. I heard they had terrible fights, but so be it. One of the primary concerns was actually, or the primary intention was to actually just build a box. The project is the Serpentine Gallery Pavilion in London. The Serpentine Gallery is a kind of an outlet of the Tate Gallery. And as such, it always invites every year an architect who hasn't built in Great Britain yet. So Toyo Ito never actually built in Great Britain, and therefore was invited to build a pavilion in London by the Serpentine Gallery. So pavilions are pretty easy, actually, right? So programmatically, they're just structures in the landscape. So they don't have to do very much, right? They maybe give you shelter from rain, and that's it. They might not have to deal with insulation. So this is a real ideal case study to look at pure tectonics, also in a structural sense, also in a material sense. So what Toyo Ito actually sort of set out as a kind of first precondition for the pavilion was that it should be a box that is not a box. So that was a design parameter. So then both Cecil Belmont and Toyo Ito ventured into a kind of a number of investigations in terms of how to not make a box. And I spare you all the kind of sketches that they did. I have them somewhere in one of my books. But the primary concern that we are looking at here is basically the concern about finding a structural system. Of course, we could actually say, okay, well, we can just do the kind of Mies van der Rohe thing like the National Gallery in Berlin. We make 4 columns, a floating roof, and we have the perfect temple. That would be the classical attitude. That would be representational, I would argue. But can we detect the Gothic spirit in the way that actually Cecil Belmont and also Toyo Ito are actually investigating their architecture? What they're trying to avoid is a kind of a classical system. Cecil Belmont also was very interested in a kind of an informal discussion. And what you see here is a number of patterns that would actually be the base pattern eventually for the structural system. And you see that there's quite an intensive kind of research in different possibilities. All of them have a kind of a particular logic to them and might be good or bad, we don't know. But what they settled ultimately is a system of a simple frame that actually would outline, basically the larger frame would outline the outer perimeter of the pavilion, and then a smaller frame would be rotated, but not rotated 90 degrees or 45 degrees, but rotated so that it divides the outer edge of the larger rectangle by a ratio of 1/3 to 2/3, which results in a kind of a non-classical, informal division. And then you would repeat that process by inserting another rectangle, and again the rectangle is rotated so that it divides the second rectangle by a ratio of 2/3, 1/3. And then the process is repeated a number of times. And then as a last process, the edges of each rectangle are actually prolonged. And what you see as a kind of a gray surface is the basically maximum perimeter of the pavilion. So now these are actually protruding out beyond the perimeter. And the last step, these edges are actually flipped over into the vertical, resulting in a quite in a pattern that looks actually quite unorganized or disorganized, but it is actually super organized. It follows a really, really precise algorithm. And here's a larger picture, and here's a finite element analysis diagram of the forces. So what results out of that crazy operation is actually a structure that in and itself is highly redundant in terms of its structural abilities. It generates a network, or let's go back to. It generates actually a network as a roof structure that is mutually supportive. It also generates vertical supports on the perimeter of the structure that are not rectangular to the roof diagram, therefore are braces in themselves. So the whole structure in itself is already structurally performative. If we would follow the kind of classical mise fin roue attitude, and we would just put 4 vertical columns and would put a kind of a flat roof on top, then we would actually have to take care of all the shear loads. Here, the structure does it for itself by its own sort of kind of constructive logic. Right? And now I'll walk you through a couple of images. And of course, for example, the 4 columns, the 4 mise columns would be possible because you would actually have to dig deeply into the ground to get a couple of massive foundations so that they don't tip over. I think in English you call them flagpoles, or they operate like flagpole columns. So that's not an option in the case of a temporary pavilion like the Serpentine Pavilion. You have to basically have an independent box that just basically drops on top of the lawn in front of the gallery. So basically what you see here is the floor diaphragm, and of course the floor gets then framed out by a joist system, which is a kind of a secondary system. Here you see actually that the floor reflects what is going on in the ceiling. Here you see how it is propped up. And as a kind of first layer, you have the tectonic system of the flooring actually coming in there. And what's happening now? There's another system that we need to actually start constructing the roof. It's basically a simple scaffolding structure that will actually support the roof in the beginning. So basically, the pavilion, the main structure is basically just made out of flat steel panels or steel plates. They are basically pre-assembled off-site and then come in larger sectional elements and then are lifted in place by a crane. Here you see the first panels going up. Here you see basically the steel plates and how they're connected. And here you see the crane actually lifting the first roof segments on top of the scaffolding. And I have a really hard time. Can you see that all right? Or are they too small? Is that good? So here's a couple of shots of basically how these steel plates are welded together. So very, very simple, very straightforward constructive methods. Here you see that one of the elements being hosted by the crane. And then there's a second material that is used in the constructive process, and that's basically glass panels that sort of provide a little bit of a shelter and protection from the elements. And these guys are lifted there too. And there's another instance how these fields are actually then filled. They're filled with steel panels. And what you see here is pretty nicely is basically the steel panels need, so that they don't buckle and warp. They need a little bit of a reinforcement on the backside. More glass. Here's one of those suction cups lifters. Basically, there's 4 suction cups that sort of suck onto the glass panel, and then you can actually lift these large glass panels into place. Here you see one of the opaque steel panels lifted into place. And that's an interior shot looking towards the roof scape before it is finished and before it is sealed off. And a couple of flooring shots. And here you see basically the last remaining panels in the ceiling being mounted into place. This is an interesting shot that basically illustrates how those glass panels are actually propped into place, and they're basically just glued in there, but with silicone. And these are a little bit larger format construction photographs where you see basically those large panels being put together. And that's an opening shot. And okay, and this is the final pavilion in all its splendor, and the interior. And as I said, it's just very simple programmatically. It's just basically a thing in the landscape. It doesn't do very much. It doesn't have heating. It doesn't have building systems. It just provides some protection. It is easy to disassemble again, which you have to do after the summer, and make place for the next pavilion to be built. Okay, this was one too much. Okay, so there, I sort of basically want to stop. But basically, just to summarize one more time, what I think what we can actually observe here is actually a particular kind of shift in a paradigm of thinking. The thinking here is not oriented towards representation or any kind of other issues that are quite important as well in architecture beyond tectonics. But the issue here really is about thinking about how can I actually construct, how can I actually use tectonics to be the main driver of the project. How can I exploit the possibilities of materials? In this case, actually steel. Steel is possible to span if it's assembled in a mutually supportive network, as we saw here. Quite a distance. It's thin steel plates that are used. The thin steel plates are only possible, and they don't wobble and warp because they're crisscrossed with other steel members. So what you get is a kind of a very intense, very rigid framework or network of steel plates, and that's why it is actually working as a structure. It also works as a structure because it actually is thought about in terms of how it is assembled in kind of pre-fabricated larger segments and then bolted together on site. It is thought about what is the maximum size of, for example, a glass panel that I can get, and how do I have to subdivide, for example, the structure so that I can have, so that I don't get fields that are too large to be filled single glass panel, and so forth and so forth. So there's a certain constructive logic behind the project that drives the project and its appearance. And what is ultimately so convincing about the project, or why I'm sort of kind of so fascinated with it, is maybe sort of the kind of the three criteria for architecture that Vitruvius 2,000 years ago was actually bringing forward, and that would be firmitas, utilitas, and venustas. So it's firmness, utility, and venustas, I would say, I would translate with sexiness, since it comes from Venus. And at that point, I want to sort of end it, okay? If you have any questions. Sure, yeah, absolutely.
Perhaps something you could address, I think, for students is this question of, I've been thinking about, in light of your presentation, the performance of representation